Bob Feet is Chief Technologist and Senior Fellow at L3Harris with over 40 years of experience in imaging science. And he's got quite a lot packed into that career, going from Kodak to ITT and Axcelis and such. He's done work with the government, the FBI, Department of Justice, on criminal cases involving image exploitation. He's authored 3 books and more book chapters and many papers. He's inaugural editor of the SPI Spotlights book series and has 12 patents, and including one that was used in the Harry Potter movies. He's been awarded the Rudolph Kingslake Medal by SPIE and is a senior member of OSA and SPIE and is a fellow of SPI. Thank you so much, Bob, for speaking to us tonight, and I look forward to your presentation.
Oh, thank you very much for that kind introduction. Yeah, I'm old. I've been around. I've done a lot of things. So thank you very much for joining. This presentation I've been building this for quite a many years. It started when things that our company did started becoming declassified, and I would start sharing in different public forums some of the things that we've done because people didn't know what our company had done right here in Rochester. And then I built it up to do a colloquium at RIT at one time, and then it's just built from there. And now it's something that I actually share with a lot of our new hires in L3Harris because the new hires don't know the legacy or the history of who we are. So the first thing I share with them is, what are our roots? Where do we come from? And we are originally the Kodak Remote Sensing Systems Organization. When I joined them back in the 1980s, we were the Kodak Government Systems Group. And that's all anybody ever really knew about us because we weren't allowed to talk about what we did. But in the 1990s, things started opening up and people started realizing that our organization was world-class at building space imaging payloads and doing the image science behind space imaging. And so we could start giving talks about that. And then I'll start talking about how we started working on commercial systems, which really opened the door for what we were able to talk about that we did at the time. We, in 1994, we commercialized a lot of our image science. We acquired a company in Colorado called Research Systems, and right now they're in the final agreements to sell off that division. So that won't be part of us anymore. In 2004, as you know, Kodak started getting into financial difficulties. And so they sold off a couple of their more profitable divisions. One was the health imaging systems, which became Carestream. And then they sold our space imaging group to ITT. And ITT formed a new group called ITT Space Systems. And they merged us with their weather satellites and their GPS satellite payloads for this organization. To our surprise, they actually made us the headquarters of this new division. Even though they had acquired us, Rochester became the headquarters for ITT Space Systems. So this was fun and exciting because now we were integrated with weather satellite systems as well as the GPS payloads. So every GPS signal you've ever received came from the hardware that our organization built. So then, of course, ITT spun us off in 2011 as our own defense company called Axcelis. And we knew they did that because they were looking for somebody to acquire us. And sure enough, in 2015, Harris acquired us. And they merged us with their satellite business, primarily down in Palm Bay, Florida, which is their space antenna systems group. They did have some weather ground processing others. And then in 2019, Harris merged with L3 to become L3Harris. And then they merged us with their organizations that do intel and cyber. But we're still the space organization within Space and Airborne. So we have about 1,200 employees here in Rochester in the Space and Airborne group. There's 3,800 employees around that total in Rochester, but the difference is in the communication systems group, which is the Legacy Harris Tactical Radio group here in Rochester. So what most people don't realize is when they see the space images on the evening news now, especially the clue that it came from one of our imaging payloads is if you see Maxar. Maxar, I'll show you later, they acquired the high resolution space imaging companies. And so anytime you see something in the evening news, and just recently I saw high resolution satellite imagery of the earthquake damage in Turkey. And those all come from imaging space payloads that we built right here in our facilities in Rochester. So We play obviously a critical role in the whole development of being able to see these high resolution space imaging images in the evening news. And so it's just fun to go through the history of how we got here. And so I actually go way back just for the fun of it. I go way back in history and I talk about the history of imaging itself. And then how did we link into that? How did Rochester link in and how did our company link into that? So I say it always starts with a hole in the wall. A lot of you are probably aware that the original imaging system was a camera obscura, a dark room. And it was in the 10th century, Al Hansen actually was the first to describe how a small hole in the wall was actually forming an image in this dark room. But it just became a curiosity. And of course, the Latin word for room is camera, and that survives today when we call these imaging systems cameras. In the 16th century, European artists were using these camera obscuras to help sketch and record portraits of people. But again, the recording was still subject to the artist's interpretation. So around the same time in the 10th century that Al Hansen was describing this, the monks were using these glass hemisphere polished surfaces that they called reading stones to help magnify the text from the biblical stuff that they were writing. And lens is the Latin word for lentil because it's shaped like a lentil bean. And around the 14th century, Venetian glassmakers realized that if they put them in frames, it would actually correct people's visions for people that were having blurred vision while reading. So the first big innovation in cameras came when the lens and the camera obscura were combined. And so, of course, the problem with the camera obscura is you needed a very tiny pinhole in order to get a sharp image. But that tiny hole only let a very small amount of light in. So if you broadened and widened the hole to make more light come through to get a brighter image, you lost the one-to-one mapping from the scene to the image and it blurred out the image. So of course, by putting a lens in here, now you could converge the light back to a point from the scene and you get a brighter, sharper image. So we can now get some brighter images in the camera obscuras, but we still can't record them. So in France, Nikifor Niepce was the first person to actually come up with a way of recording an image. And first, he found the materials such as silver halide would darken as light exposed on them. Now his problem is that he could get an image, and it took a very long time for the image to form. It took a very long exposure time. And as he'd go around and show people the image, it would continue to get darker and darker and darker as the light exposed it. And so he had to find a way of fixing it, of stopping this process. And so he finally found some solvents that would actually stop this process. And so in the lower left here, you see the very first picture he took that he was able to fix and stop the process. And so he could actually preserve the image. And it was an image outside of his estate, window at Le Gras. And so with image enhancement today, we can actually enhance that image because it's poor quality. And we can actually see what's in that image. And again, it took between 8 and 20 hours to expose. So one interesting thing that I like to point out to people is if you'll notice, the two facing walls here, or opposite facing walls in this image, are both sunlit. And that's something you wouldn't see today if you took a picture outdoors, like in an urban area. And that's because the sun is obviously going to illuminate the same sides of the buildings from where it is in the sky. And this is because it took 8 to 20 hours to expose. And so as the sun moved across the sky, it was exposing the different surfaces of the walls. And so you get this weird effect happening. And his estate still exists today that he pointed the camera out and took a picture of. So he teamed up with Daguerre, and they were working on different methods to reduce the exposure time so that they could actually get portraits taken of people and they wouldn't have to sit for 8 to 20 hours to get exposure. Unfortunately for Nikifor Niepce, he died a few years later, and so Daguerre took credit for all of his work. And so it's only fairly recently in history that Nikifor Niepce is given credit as the inventor of photography. But Daguerre was able to reduce the exposure times quite a bit. And it was through a process that he called the daguerreotype. And so on the lower left here, you see his very first daguerreotype. And then in the lower right here, just a year later, he took a picture outside a window in Paris. And that exposure only took 7 minutes, but it's still long enough that it blurred all of the traffic that was on the road. So there's horses and carriages, but they got blurred out during the 7-minute exposure. But there's a gentleman here that stopped to get his boots polished. and he stood long enough that he didn't blur out in the image. And so he's the first known person captured in a photograph. Now, some people think that there might be a little girl peeking out the window here. And so that might also be another person in the picture, but it's not clear if that's a little girl or just something sitting in the window. But that's clearly the guy getting his boots polished here in the picture. What about color photography? I'm not actually going to talk much about color photography for quite a while because it was a very difficult and expensive process. As you know, you have to basically filter out all the wavelengths of light except the red, the green, and then the blue. And so you get very dark images when you do that. And the chemical process for doing that was even more difficult at the time. In 1861, Thomas Sutton produced the very first color photograph. It was a transparency. He had just as some of the slide projector film we used was. And then the first print came in 1871. So the first consumerly available color film was Kodachrome, which was slide color film back in 1935. But it wasn't until the 1980s that more color pictures were taken in black and white. And again, they were more expensive, they were lower quality, they required brighter lights. And so people in general just stuck with black and white photography for most of history. So what about getting the pictures overhead? So the first guy to do this was a Frenchman that went by the trade name Nader. And he went up in a hot air balloon with a camera to take pictures. And so this is some postcards he was making to advertise his business. Unfortunately, all of his originals are lost. The very first earliest existing aerial photo was taken over Boston by James Wallace Black, again, from a tethered balloon. We do have some pictures from Nader that came later. You can see they're poor quality, but I think it's interesting that he labeled the streets just like we do in Google Maps today, because it's hard to get your perspective when you're looking at an overhead image. Now, his postcards didn't really tell you the truth. He didn't just simply put a camera on a tripod up in a hot air balloon. He actually had to take a whole photo lab up with him. And so it's this very large room that would actually be attached to the balloon and go up. And one of them came crashing down, and it made the news when it came crashing down because it was a big deal. So this was how overhead photography was made at the time. But now we're going to go to Rochester, New York, because as you know, the big game changer was George Eastman inventing roll film. So George Eastman was over in Germany and saw that they were using a dry film process. And he came back to the United States and said, well, this obviously is easier to use than the wet chemical plates that people used. But he wanted to go a step further because it was still difficult to use the dry plates. And so his big invention was putting this dry emulsion process onto plastic roll film. So you could actually spool it up and put it in a small, very lightweight camera. And so that was the Kodak camera that he invented. And of course, the famous phrase, you press the button, we do the rest, because it was that simple. Well, now that we've got these small lightweight cameras, we don't have to carry a photo lab up into a balloon to take pictures. Arthur Batout in France was the first person to say, I can put one of these on a kite. And so he flew one up in a kite. The problem is, how do you push the shutter if the camera's all the way up on the kite? And so he actually invented a method where he would light a fuse, and the fuse would then set off an explosive that would make the shutter trigger when it was up on the kite. And so again, here's one of his earlier pictures. Lieutenant Hugh Wise was the first to experiment with this for military purposes up in the very northern stretches of New York. He again attached cameras to kites and floated them up to see what we could do with surveillance or reconnaissance. Not very practical because you can't really point the kite and you kind of get what you get. But again, he was the first to experiment with it. Probably the most famous kite picture, maybe the only kite picture most people have ever seen, is the photograph that typically shows up in history books with the San Francisco earthquake in 1906. George Lawrence actually had a huge panoramic camera that he would float up on the kites, but he needed many kites in order to get his heavy camera up. And so he actually patented a way of concatenating these kites together, and he used 17 cameras. You see a picture here of the kites to get enough lift to lift that camera high enough to get the pictures over San Francisco. What about rockets? So Alfred Nobel was one of the earliest pioneers in putting cameras on rockets. So of course, Nobel was famous for inventing dynamite and the Nobel Prize. But one of the problems he had was that the rockets vibrate, they shake, and so they blur out pictures. And so he would get some nice pictures that weren't blurred out, but they were typically very low altitude before the rocket really started shaking and blurring it out. So Alfred Mall in Bavaria actually patented a gyroscopically stabilized camera. And so this actually held the camera much stable and didn't shake as much. And so he could get much clearer pictures at higher altitudes with these cameras on rockets. So we get to the pigeon cameras. So these cameras can, with a roll film, can be made small enough and lightweight enough that you can actually put them on homing pigeons. And so Julius Neubronner had this clever idea, just putting cameras on homing pigeons. And since they're homing pigeons, they come back. At least that's they do in theory. And he put the cameras on timers to take a picture every 30 seconds. And he'd fly these pigeons around, collect the cameras, and expose the film to see what he got. And this is where he was taking pictures over a conference site. And then he would take the pictures, print them on postcards, and sell them for people to see the overhead images. So it's no surprise that the first documented aerial photo from an airplane is from the Wright brothers. And so the first documented aerial photo was one flight they did in Italy. And they literally held the camera in their lap. And so you can see one of their boots here, just from holding the camera in the lap as they took pictures. So a big advancement in the overhead images, especially aerial photography, was World War I. And so the British were the first to pioneer aerial cameras for airplanes that, as you can see, they would attach them to the side of the plane for convenience to the pilot to take the overhead pictures. As the United States got involved in the World War I, then Kodak took the British design and improved upon it. And so by the end of the war, the Kodak K1 camera was the camera of choice for overhead imaging. So clearly in World War I, they were looking for all the trench networks. They wanted to be able to map out the trench networks and then be able to know where to shell those trenches to drive the soldiers out of them. And so you can just see in the pictures here, you can actually see the devastation from all the shelling that occurred around the trench networks, trying to get the soldiers out of there. So one problem they still have with film, Kodak film, is that you still need bright lights to get a good exposure, a good bright image out of that. And so Kodak was developing film that was more sensitive to lower light levels. And the first aerial night image was taken by Goddard over Rochester, New York. And in order to get enough light to actually see the city itself, they actually exploded an 80-pound flash powder bomb over the city, which I gotta believe terrified the people when they saw it because they didn't know what was happening. I went ahead and labeled the streets here so that you can see the area that this was taken in. The Genesee Brewers in the lower left, and basically this is the intersection of Lake and Lyle, where they took this picture. In 1931, they took another picture over New York City, and again, I suspect the people weren't warned about this, and so it probably terrified them when they saw this big flash in the sky. So made big news in 1930 when an aerial photograph could be taken high enough that they could actually see the curvature of the Earth and measure the curvature of the Earth from the photograph. Now, with regular film, you can't do this because the haze in the atmosphere will just completely reduce the contrast of the curvature of the Earth. But Kodak was developing infrared film, and infrared light penetrates haze. And so you can actually see through the distance in infrared film and see the curvature of the Earth, and they were able to measure it. And so that put an end to the Flat Earth Society, unless you thought this was a fake photo. So, but it made big news. This is on the front page of the New York Times when this happened. So World War II, again, advanced the overhead cameras. They wanted high resolution from higher altitudes so they wouldn't get shot down. And they also wanted wider formats so they could get larger areas for reconnaissance and surveillance purposes. And so again, Fairchild F-24 camera was the first really well-developed camera that people used. And then as the United States got involved in World War II, then Kodak took upon that and improved upon it. And the Kodak K24 camera became the reconnaissance camera of choice by the end of the war. This is an interesting photo I found. I'll talk about the Hawkeye plant in a little bit. That's where I began my career, was at Kodak's Hawkeye plant. This was a actually prototype camera that was built at Kodak's Hawkeye Works to show the Air Force that if they could fly an aircraft up to 10 miles, Kodak could build them a camera that would take the reconnaissance imagery that they wanted. You can see it's a big, heavy camera, but again, it was just a prototype to show the Air Force that we could build it if they could fly that high. This is just one of the aerial photographs of World War II that I like to show. We saw in the movies and TVs, you see that when the Nazis brought prisoners to the concentration camps, they would typically divide them into two groups. So one group as prisoners and then the others to be executed in the gas chambers. And this was just an aerial reconnaissance picture where they actually captured this happening. They captured a group of people prisoners being brought to the camp, and the other group being brought over towards the gas chamber and the crematorium. So a very sad picture, but again, this was proof of the Nazi atrocities that were happening at the time. Well, after World War II, of course, you always heard about the race to get the rocket scientists. The Soviets were trying to get them, and the Americans were trying to get them. And the V-2 rocket scientists that came to America, a lot of them went to White Sands Missile Range to work on the Rocket 2 program. And in 1946, they had the idea of attaching a camera to one of the V-2 rockets and shooting it straight up to see what we get. And it reached a peak altitude of 105 kilometers, which is great because the definition of space is any altitude higher than 100 kilometers. And so this was the very first image of the Earth taken from a space altitude from that V-2 rocket. Along comes Sputnik in 1957, which shows you can put artificial satellites in orbit around the Earth. And of course, everybody immediately started wondering, can you put cameras on those satellites to take pictures, again, especially for reconnaissance and surveillance? The problem is of course, you put Kodak film on the camera, you need to get it back to Earth to develop and analyze. And how do you do that? And so that became a problem, was how are you going to get high resolution images back from orbit as well? Well, we have television cameras at the time, so let's talk about television for a minute here. In 1927, Philo Farnsworth invented his image dissector in San Francisco. In the lower left here, you see the building where he made his first TV transmission. It still exists at 202 Green Street. So he transmitted the first television signal and then filed a patent for the television camera and process. He got into a legal battle with RCA. They claimed they invented television, but in 1936, he won the lawsuit and he became the known inventor for television. So he started looking for a place to build a company and to start manufacturing his equipment. And he found that in Fort Wayne, Indiana, there was the Capehart Phonographic Company that had just folded up. It had the right manufacturing facilities, people ready to work. And so he decided to set up his shop in Fort Wayne, Indiana. And in 1951, a company, ITT, purchased his Farnsworth Television and Radio Corporation. And so now ITT owned all the intellectual property for the television technology that he had developed. So the very first image of the Earth from a satellite is from a television camera back in 1959. It was an RCA television camera. Not very good, very poor quality, but again, it was first attempt to take a picture of the Earth. A year later, the Tyros satellite was developed to use a television camera for meteorological purposes. And you can see it's a much better image. And it did prove that these satellite images from a television camera could be used for meteorological purposes. And so that paved the way for a program called Nimbus. And so Nimbus satellite was the very first meteorological satellite program, and ITT had the contract to build the cameras, the television cameras for this meteorological system. And so they built a high resolution infrared radiometer to image the clouds and the weather systems as well. And that was built by ITT in Fort Wayne, Indiana. Well, if we fast forward to today, in our company, that's where we have this very long and very large legacy of weather satellites within our company. And it all started with Nimbus 1 up in the upper left corner here, but it led to Nimbus. And today, the more famous weather satellite images you see are from the GOES satellite. They're the geosynchronous satellites that stare at the Earth and take all the hurricane pictures that you see and all those pictures. And the Fort Wayne group in our company has built all of those as well. They've more recently shown that their technology can also be used for missile warning and missile defense programs. And so they've actually, in Space Development Agency, they've got a number of very large contracts now to develop these systems for missile warning and missile defense as well. So they've been doing very well. Well, let's talk about digital imaging, because we know digital images are how we see satellite images today. Well, first digital image was in 1957. It was by Russell Kirsch, who just passed away. It was either last year or the year before. He just recently passed away. But he was at the National Bureau of Standards, and he basically invented the first scanner. And so what better image to scan in than an image of his young newborn son? So he scanned it in, stored it in a computer as zeros and ones, and then read it back out and printed it. And so that was the very first digital image that was captured and stored and that he could be printed. In 1975, famously, Eastman Kodak, Steve Sass and Eastman Kodak invented the digital camera, but they didn't know what to do with it. Steve Sasson said he was 100% prepared to tell management the what. He was not prepared at all to talk about the why. And so when the managers asked him, why would we build a digital camera, he didn't have an answer for them. And so, of course, Kodak shelved it. And it was very impractical at the time, but Kodak didn't do anything to develop the technology any further. So for surveillance and reconnaissance, the fairly newly formed CIA in the 1950s realized that the only way they were going to get high resolution surveillance and reconnaissance images was to fly them on a high altitude aircraft. Since we didn't have any practical way of getting film back from space, we just have to fly very high altitude aircraft that the Soviets couldn't shoot down. So the U-2 was designed not to be undetected, because they knew the Soviets would detect them with their radars, but they would fly at 70,000 feet where the Soviet anti-aircraft missiles couldn't shoot them down. And the U-2 program, the first flight was in 1955, and it proved very successful. It proved that there was no bomber gap. The Soviets claimed they had way more bombers than they did. And so it proved that they were basically lying. They didn't have all the bombers they claimed they had. So we weren't as in much trouble as we thought. That lasted until 1960, when an errant anti-aircraft missile just happened to hit Gary Powers' U-2, and it shot it down, and he survived. But the United States had to admit that they were flying these aircrafts over the Soviet Union, and so that they had to stop flying them. In August 1960, Gary Powers was sentenced to prison, and our follow-on high-altitude reconnaissance aircraft was the SR-71, but that didn't fly until 1964. And the SR-71 was designed to be more stealthy, so that not only could the Soviet anti-aircraft missiles not hit it, because it flew so high, but the radars wouldn't be able to detect it either. So it looks like we have this 4-year gap in our reconnaissance capabilities, but it's interesting that on the same newspaper page where Gary Powers is sentenced, we see another headline that says space capsule is caught in midair by U.S. plane on re-entry from orbit. And what's all that about? Well, the United States decided that they could put Kodak film in space and spool it up in a capsule after it captured the images, and then jettison that capsule back to Earth. It would parachute back to Earth, where an airplane would snag the parachute with a hook, and they would reel that film bucket back into the aircraft, where they could take it back to a facility for processing. And so it was a classified program called Discover, or Corona. The cover story was Discover, just a science mission. And so Kodak had the contract to build the very unique film for this system. It had to be very, very thin, had to be very long. It had to survive the very cold temperatures up at the high altitudes. So it was just a whole new invention for film that had to be developed. The actual camera system for Corona was built by a company called iTech. So Kodak did not build the camera system, but they did invent the film that would successfully work on the Corona system. And this was classified until 1995. So before 1995, Kodak could not talk about its involvement in this program. So the first successful capture that you saw there in the newspaper was the 13th mission, but because they were still trying to figure things out, there was no film on it. It was just telemetry equipment on board. So it was actually the 14th mission where they actually put film on board, and they successfully recovered it. And the first image they took over the northeast corner of the Soviet Union, they saw this very long runway up there that they didn't know existed. And this was critical because this is a long enough runway that they could actually launch nuclear bombers from the site into the United States, into Alaska. And so it was very critical that we knew that this existed. And so right off the bat, the Corona mission is paying off. Now you can see the quality isn't great. The resolution's about 40 feet in the original images. In 1967, with improvement with the film and the optics, they could get the resolution to about 10 feet. Again, not great by what we see today, but it was great for being able to use it for reconnaissance. So, of course, when you have classified missions, you're going to get UFO sightings. And this is one of my favorite stories. So they could only snag the parachutes in the daytime when the pilots could actually see the parachutes. And so they could fly in with their large hook and snag it. But they thought, what if we wanted to actually cover the capsule, the film capsules at night? How can we get the pilots to see them? And somebody suggested putting a strobe light in the parachute. And so they were running some test flights where they would jettison the capsules and try to capture them off the coast of California using these strobed parachutes. Well, of course, the people off the coast of California, when you see something strobing that's dome-shaped, the only explanation is that it's an alien visiting us from another planet. So that's what the newspaper reported. And this is actually an artist rendition of the flying saucers flying off the coast of California at the time. And you can see that it actually looks like a parachute that may be strobing as well. So you can see how they interpreted it that way. But of course, you know, most of the UFO sightings through history we've learned are actually from programs that the US government wasn't talking about. So now I'm going to talk about the origin of the organization that I work for. It all started as a group called Special Programs within Kodak, and it was set up at the Lincoln plant out by the Rochester Airport to process the U-2 and SR-71 film. And when they got involved with Corona, the Lincoln plant facility wasn't large enough to handle the film buckets and the processing, so they moved the whole organization over to the Kodak Hawkeye plant. And that's north of the city on Driving Park. I know many of you have probably been there in the past. We vacated it in 2011, but this is where I began my career for almost 20 years. My office was right in the northeast corner of the Hawkeye plant. Unless you had the clearances to know where the film was being processed from the Corona satellite, you only knew that it was being processed at a place called Bridgehead. And of course, you can see that they called it Bridgehead because it's a building at the head of a bridge. So they weren't too covert about it. But what's interesting is this is now historically the very first mission ground station from the National Reconnaissance Office, because this is where all the film was brought back for processing. This is where the first phase, a lot of the first phase analysis was done as the film was processed and people could look at it. They made very, very high quality duplicates of the original film from space so that the analysts wouldn't be handling the original film from space. And then it was all flown down to the National Photographic Interpretation Center in Washington, D.C., which now today is part of NGA. It was down in Building 213 in the Washington Navy Yards, which has since been razed. The building doesn't exist anymore, but that's where it all came. We were also responsible for the final image quality. So when people look at the film and they see the image quality isn't great, they're going to blame the film. They're going to blame Kodak and the film, even though it may be a problem with the camera itself. And so Kodak then was responsible for understanding all of the parts that came together to form that image quality. And so I'll talk about that later, because that was another big part of our organization. So that's how we were getting high resolution images back to Earth. But what about the moon? We can't deorbit a film bucket from the moon. And so the early attempts were basically, again, using a television camera, but the television cameras didn't give you high enough resolution unless it was really close to the surface. And so Ranger 7 is a satellite where they actually purposely deorbited into the surface of the moon to get high resolution images of the surface of the moon. And so this is an image that was taken from Ranger 7 2.5 seconds before impact. So there was in the early 1960s, there was another classified program that Kodak was involved with. So Corona was the CIA, Samos was the Air Force. And what the Air Force wanted was a system that would get intelligence back sooner than the Corona program, because Corona, you take the pictures, but you still have to wait until you fill the film bucket. Then you jettison it back to Earth. It would have to get processed, and then it would get sent down to Washington for analysts. And by then it might be old history. And so with the SAMOS program, they said, well, what if we put a film processor on the satellite so we can actually process the film, scan it in, and then radio transmission that scanned image back to Earth, and you'll get a lot quicker than waiting for that whole film bucket to get filled up and sent back. And so again, this was a mission called SAMOS, Satellite Missile Observation System. It was canceled after 11 missions because they were still poor quality images because they had to be scanned and then electronically transmitted. But the good news is that the Air Force allowed Kodak to transfer the technology to NASA. We didn't have to keep this technology classified. And so for NASA, we built a satellite payload called, or satellite, the imaging payload for the Lunar Orbiter. And it used this very same technology. And so here's the Lunar Orbiter camera system being built at Lincoln Plant at the time. And it flew and orbited the moon. And in 1966, this is the famous image of the very first image of the Earth from the moon. And it was taken with our Lunar Orbiter camera. And again, because we process the film on the satellite and then scan it to transmit it back to Earth, you can actually see the scan lines in this image. Now, since then, people have processed the image to remove the scan lines, but I like keeping them in so that you see historically the original image and you can actually see the scan lines in them. So we're back to the reconnaissance of the Earth using satellite systems. The Corona system, again, you saw the image quality wasn't that great. Kodak proposed, rather than using a lens camera system, they could build a telescope camera system. And by using a telescope, you would get much higher quality images from the satellite. And Kodak was awarded the contract for this, and it was a classified program called Gambit. And it wasn't declassified until 2011. But this is the first time Kodak had the contract for the entire imaging system. So we built the whole camera system, the telescope, the film. We did all the film processing was still done at Hawkeye. And you see a Gambit bucket here at Hawkeye plant that's being delivered to Hawkeye. So a very successful program, very high resolution. Even though the program's been declassified, the National Reconnaissance Office hasn't released imagery from Gambit yet. They still think the quality is sensitive and the areas that we took images of is sensitive. So all they'll say is that the imagery was, the quality was, the resolution was better than 2 feet. That's all they'll admit to currently. But we'll keep waiting. At some point, I suspect they will release some and declassify some so we can see them. Now, the Gambit program was for high resolution imagery. So think of it as a zoom camera, a zoom lens on a camera, because you're zooming in to get high quality. There was a sister program called Hexagon, where you were actually looking at more of a wide angle lens, wide field of view, so that you can see more area. And this is more important if you want to see what's happening agriculturally, how are crops doing and other areas as well. And since Kodak was building the Gambit payload, the contract for the Hexagon payload was given to a company in Danbury, Connecticut called PerkinElmer. Now, this is interesting because these are the two programs that were classified programs that were flying then. You had Gambit and Hexagon. And today, the two companies in the United States that build high resolution, large imaging space payloads are us in Rochester and the Optics Group in Danbury, Connecticut. And so it's still the two major players today that you see here. So with Hexagon, you can see in the lower left here, you can see how large this system is. You can see a person standing next to it here, very, very large. And you can see it's got 4 of these gold buckets. So it could fill one bucket with film. And when that filled up, they could jettison it back to Earth. But the satellite could still be used because it still had 3 more buckets it could fill with film before the satellite became defunct. Now, because this is lower resolution, wider field of view imagery, they did release the Hexagon imagery. And so here you can see an example of a Hexagon image. And it flew successful missions all the way up until the very end. The very last one, they launched, blew up on the launch pad. But until then, they had 19 successful missions. So the last system that the NRO has declassified, and that was just in 2015, is a classified program called Dorian. The cover story was the Manned Orbital Lab. But again, they're looking for ways to get information back quickly, much more faster to Earth, more quickly to Earth than waiting for these film buckets to come back. So they had the idea, well, what if we actually have astronauts in space that will take the pictures, they'll process the film, they'll look at the film, and they'll report back to Earth what they see. And they can do that very, very quickly. So they actually had a living quarter, they had a photo lab, they had all of this on the satellite. And this was big for our company because we were given the contract for the entire optical system. So again, very large telescope system, very large imaging system, the processors, everything on there was a very large contract for Kodak at the time. It required a new facility to be built. And so we did, this is a very poor diagram of the new facility, but we have that facility and we still use it today. And so we still make very large optical systems in that facility, and that's thanks to the Dorian program. Now it flew one mission, but it was unmanned just to test things out. And then the program was canceled in 1969. There were a lot of cost overruns. And of course, with the Vietnam War going on, the government was hard pressed to cut back costs where they could. And they were always nervous about putting people in space on classified missions, because if something were to go wrong, you'd have to admit that, you know, you had people in space when you didn't want to admit they were up there doing things that we didn't want to disclose. So that's the last government program I can talk about that we've been involved in. So stay tuned until other things get declassified. But I'm going to jump to our commercial systems. And this is actually very exciting in many, many ways. Foremost, that we can talk about this. And the public in general became aware of our technology capabilities because of our work in the commercial systems. And this all changed in 1992. The Soviet Union had collapsed and Russia was looking for ways to make money. And they started selling their classified images on the open market. And it turned out there was quite a big appetite for high resolution images of the Earth. And so the aerospace companies in the United States wanted a piece of the action, but the US government originally said no, because any high resolution space images you take will be classified. And so finally, the Land Remote Sensing Policy Act of 1992 allowed companies to apply for a license for high resolution space imagery, as long as the resolution wasn't better than a 1 meter ground sample distance. So a lot of companies, more than 20 companies filed for licenses. Only 4 really put a lot of serious effort into it. Boeing's, and you'll notice these companies, Ball, Lockheed, Orbital Sciences, Boeing, all spun off a company, a commercial entity company that then would contract them back to build the systems. And Boeing spun off Resource 21, but they never actually flew a system. But Ball, Lockheed, and Orbital Sciences all spun off companies that actually did end up flying systems as well. And so over time, I put this slide together because over time, they started merging and getting acquired. And finally, by 2013, Digital Globe had acquired all of the existing high resolution space imaging companies. And then in 2017, Maxar bought Digital Globe. So today, Maxar owns all of the highest resolution space imaging systems that are flying today. The very first one to fly was one that we built. We had a contract with Space Imaging, which was the Lockheed Martin spinoff, to build the camera system. And so we built again, a space imaging system using a telescope that had a very high resolution panchromatic black and white sensor. So that's where we got our 1 meter ground sample distance resolution. And then we had a multispectral sensor that would capture blue, green, and red for color, and then near infrared so that we could look at crop health as well. Now, because it's multispectral, it's lower resolution. And what we would do is we use the color information from the color image to colorize the high resolution black and white image. So even today, the images that you see, the color images you see from the satellites aren't the actual color images that were acquired. They're the high resolution black and white images that have been colorized using the color information. And so again, you can see the detail here on the right here, the color image of the Washington Monument from the ICONOS satellite. Now, this is big because I'm an old timer. It's not a big deal to younger people today, but I like to point out that before 1999, before the system existed, to see this image on the right, you had to have a top secret government clearance. After 1999, anybody can see it. And so that was quite the game changer. So just to show you, at the time in 1998, the best digital camera you could buy was the Kodak DC-260, which had a 1.5 megapixel sensor in it. The Iconos satellite with one picture would capture almost 190 megapixels, but we could scan this to capture more ground information. So one image could have 6,200 megapixels. So this was a monster of a digital camera that we built for the space imaging system. The second system to fly was QuickBird. QuickBird Earthwatch had the advantage that because they were late to the game, by the time they launched QuickBird, the US government had allowed the best resolution to drop from 1 meter to 0.5 meter. And so they just flew it in a low orbit, and so that it could take higher resolution images. Now, our company built the sensor system for this. We didn't build the actual optical part of it. But I like this image of the Statue of Liberty. Number one, it's a great image of the Statue of Liberty with 2 feet ground sample distance. But it's also about the same distance from the satellite to the Statue of Liberty as it is from Rochester to the Statue of Liberty. So it gives you an idea of the great quality pictures you're getting over these long, long distances as well. Let's just show some quality over time. This is the Corona satellite on the left. At the time, it was a top secret image, about a 3 meter ground resolvable distance in it. And then, of course, Iconos, I watched them on. You can see scaffolding on it. There was some work being done on it, and that was 1 meter GSD. And then GeoEye-1 was a system we built for the 0.5 meter ground sample distance. And this is the full color image. And this was from Barack Obama's first inauguration. And I like this picture because my cousin actually attended the inauguration, and she told me she was standing by the Washington Monument. So I know she's one of the people in this picture. I can't quite figure out which one she is yet. But again, it just shows the advancement of the quality over time. So in 2014, we launched WorldView 3. That was the space payload we built. By then, we had lobbied with Digital Globe to allow the resolution to drop to 1/4 meter GSD. And this is all from international competition. Other companies are building systems that can encroach on the resolution of the US systems. So we want to stay ahead of that so that the US can obviously still have the best systems out there. And so this is just a nice image at 0.3 meter GSD of the Capitol building. You can see the cars and the people walking around, just to show you the nice quality there. So WorldView 3 actually had a shortwave infrared sensor on it. And this just shows, again, I mentioned earlier that infrared light actually penetrates haze. Well, shortwave infrared light penetrates smoke as well. So if you look at the picture on the left here, you'll see a normal color image, but on the right, you'll see the picture taken with the SWIR sensor, where again, the light penetrates through the smoke. So you can actually see where the fire is through this image. The last system we built was the payload for WorldView 4. This is the first image that they took. It was the Olympic site in Tokyo in 2016. And again, just to put it in perspective, the iPhone 8 camera at the time had a 12 megapixel camera in it, which most iPhones still have today. And our camera in a single snapshot would take an 1800 megapixel. But again, if we scan the ground, we could have a single snapshot that would have about 500,000 megapixels in one image. So these systems that we built just soak up data. They just take lots and lots of image data and send it to the ground. This is just to show you the systems that we built. Again, Iconos was the first, and then we built the sensor and electronics for QuickBird. Those two aren't operating anymore. QuickBird was deorbited. Iconos actually spent its fuel, so it's just going to deorbit naturally, and they expect that to happen around in the 2040s. The rest of them are still flying, except the most recent one. Unfortunately, it had a gyro failure, so they couldn't point it. And so they eventually just deorbited it in 2021. But the rest of them are flying. And as you still see, the highest resolution space images that are taken today all come from one of these systems that we built here in Rochester. Now, I unfortunately have to say that's going to change shortly. Digital Globe, now Maxar, their next generation of systems is called Legion, and we did not win the contract to build the Legion systems. So that went to Raytheon. And the first Legion system is slated to be launched at the end of this month. And so those will be comparable GSD. They'll be 0.3 GSD, meter GSD like these. But now when you see a Maxar image that's at 0.3 meter GSD, in the future, you won't say 100% for sure that it came from one of our systems. But right now, we can still say that. So the biggest game changer for all of us here was in 2008 when Google signed a contract to integrate the GeoEye-1 images into their maps. And why that's so important is because right now, we can look up any high resolution space image anywhere on the earth on our phone for free. So it's free, easy, we have full access to the earth, and it's all because of this agreement in 2008 that Google had with GeoEye. So before this, we could see the images, but we were kind of at the mercy of the people that had bought them and put them on a website or put them on the news. But now you can see any place, anywhere, and it's all because of this agreement in 2008. It wasn't really that long ago, so it's still fairly recent in history that this happened. Now, when I say anywhere on the earth, it wasn't quite true at the beginning, because with US military bases, they blurred the imagery, and we had an agreement with Israel that we would blur the imagery over Israel. And it would also blur out the Palestinian regions as well, just blur out the entire region. So in 2020, that agreement was abandoned. So now you'll see high resolution images of Israel. But at the time, those were the agreements that we had. So what's interesting is when all this imagery becomes available on Google, now people start looking around. First thing people did was look for their house, right? I know I did. First thing I did. But then people start snooping around, looking around different places of the earth, and they start finding some really weird things. And I'm just going to show a few of them that I found more entertaining. One is that people started noticing these large concrete arrows around the United States. And of course, one of the theories was that must be showing alien aircraft where to land, right? Because everything goes back to the aliens. But actually, it's fascinating. This is an artifact of the very first US postal transcontinental airmail route. What they would do is they would put a tower, and you can see a shadow of a tower in one of these here. They put a strobe light on top of a tower. And so the pilot would fly to the strobe light that he saw flashing. When he got to the tower with the strobe light, there would be a concrete arrow on the ground that would tell the pilot which way to point the aircraft to find the next strobing light. And so they would do that. They would point their aircraft because there's no GPS, there's no radar, everything is being flown by line of sight at this time. And so they would just fly in that direction until they saw another strobe light. And then the arrow would tell them where to fly next. And so a lot of these are still out there. The remnants of this still exist. Another one is this large array of concrete crosses just west of Casa Grande in Arizona. It's a very well-defined regular array of concrete crosses. And so the theory was this was being used for the classified Corona satellite program for them to calibrate out the geometric distortions in the camera, because the distance from one of these concrete crosses to the next was known exactly. And so if you can measure it in your film and you know that the distances are being distorted optically, you can actually then correct for it. If you take an image of this test target and you know what the actual distance is, you can calibrate that out. Now, the truth is, once the whole Corona space program is declassified, they found no evidence that the Corona satellite program ever used these test targets. They were used by the US Army for their mapping purposes, but not the Corona satellite program. But what's interesting today is if you go to Google Maps and you go to one of these crosses, it's still going to say Corona satellite calibration target because the name's stuck. But it's very likely the Corona satellite program never used these because there's just no documentation that they did. The last one I thought that was interesting that I want to share with you is that people noticed that out in the middle of nowhere in the Everglades was this long concrete strip. And so if you zoom in on it, it looks like it's a runway. And so again, it must be a runway for alien aircraft. And it's out in the middle of nowhere because they don't want the public to know the aliens are landing on Earth, right? So I don't know why everybody jumps to aliens, but it turned out this has a fascinating history. In the 1960s, when supersonic transportation looked like it was going to be the future, the United States needed an airport that would be a hub for the supersonic transport. they needed it to be away from public areas since they create sonic booms. So they thought, what better place to build it than in the middle of nowhere in the Everglades, where the sonic boom won't bother people. So they started building it. They got one runway built. And after the first runway was built, there was enough protest about building an airport in the middle of the Everglades that was obviously destroying the environment that they shut it down. And it was actually a good thing that they did, because as we all know, supersonic travel did not become the future of air travel. And so it would have been a lot of wasted money anyway. But the one runway that exists is still used as a training center today. So this is an interesting story that I saw. I was watching 60 Minutes and I just loved the story because I didn't expect it. But it's archaeologist at the University of Alabama was looking for the lost amphitheater in the ancient Roman city of Portus. So Portus is west of Rome, and they knew that there was a Colosseum there, but there was no evidence, archaeological evidence of where this Colosseum existed, where it was located. And so she then started looking at satellite imagery, and with the near infrared imagery, and remember, near infrared is used for crop health, she could actually see a circle of poor crop health in one of the farm fields. And she sent a team out there and they dug, and sure enough, they found the foundation of this lost amphitheater in this farm field. And it turned out it was because the foundation of the amphitheater was all a rock bed, and it prevented the roots from growing deep into this area. And so that's why they were unhealthy, is because they couldn't grow deep. Today we see satellite imagery, as I mentioned, with the earthquake. Almost everybody's showing before and after pictures. I thought this one was interesting. This was right before and after the shutdown from COVID-19. And so here's the Phoenix Sky Harbor Airport rental car lot. And you see it's pretty empty. People are using rent-a-cars. And then March 16th, you see the rental car lot is entirely full because nobody's traveling and nobody's renting cars anymore. This is from the Beirut explosion. Before and after, you can see the crater that was created, and you can see this cruise line that was knocked on its side, all in the satellite imagery. So the commercial satellite imagery, a lot of companies are involved today, building systems that fly high resolution systems. Again, none of them are at the highest resolution that we build currently. But again, it's very proliferated. So just because you see a satellite image doesn't mean it came from one of our systems, because a lot of people are building them now today. We did make one for a company called Black Sky. So if you see an image from Black Sky, especially if they tell you it's from Pathfinder 1, then that is a imaging payload that we built. That just shows you kind of where we're going in our technology. As I mentioned, with the Dorian program, we had a very large optics facility built. We still use it today. We still build very large telescopes for our imaging systems, whether they be looking out into space or looking at the Earth. But the key is really to get the weight down, which saves launch costs, get the timeline down while maintaining optical quality for these telescopes. And as time goes on, obviously, we are building larger and larger systems as well. It's just some examples, some of the technologies we're doing today. Additive manufacturing for optics. In our sensor electronics, we're making them smart. We want them to be more autonomous. So some of the decision making can be done on the sensor systems themselves as well. And then for our telescope systems, one of the things we're looking at is, can we make the mirrors faster by replicating the optical elements? And can we also make them out of material other than glass? And so we're looking at the composite material, just like they use for the fighter jets. Can you use that instead of glass for the mirrors? Now that has a lot of challenges. It has a lot of advantages in that you're not limited to the size of the glass mirror that you can make. But it also has a lot of material challenges that glass does not have. We built systems for NASA. Famously, we built the primary mirror for the Hubble Space Telescope that did not fly. We built the backup mirror. Perkin-Elmer built the primary mirror in the telescope for Hubble, and as you know, that primary was not made correctly, and so the original imagery was blurred, and so then they had to correct it. The primary mirror that we made was made correct to the right curvature, but it's sitting in the Smithsonian today, so not flying in space. For both Chandra X-ray Observatory and the James Webb Space Telescope, we had the contract to assemble, integrate, and test the whole thing, make sure it worked. We are building the optical telescope system for the Roman Space Telescope. And then we have the contract to build the engineering development unit for the future NASA program called LISA. We also make a lot of optical elements for the ground space telescopes, but just because we have a great optics capability, manufacturing capability. And so a lot of the mirrors for the ground telescopes were built by us as well. So now in the remaining time, I'm just going to talk about our image science here. I'll go through this fairly quickly. It doesn't have a long history as our payloads are a lot of the elements of it. Our image science organization, as I mentioned, it actually started in the 1950s when we were responsible for all the quality of the airborne systems. But the formal group was actually formed in 1970. It was called ICA, Image Chain Analysis Group. And the reason being is because we were responsible for understanding the impact to image quality of every element of the imaging chain. And so here, this is a cartoon that I had made when we were briefing this for the ICONOS program in the 1990s. So you see there's a hard copy generation, because back then a lot of people still wrote a lot of the imagery to film, which they don't do today. But that's why this cartoon was made a long time ago. This just shows some of our capabilities. I'm not going to go through this, but just a wide range of capabilities, image quality predictions, system modeling, et cetera. So this is a cartoon that I use a lot because our capabilities in the imaging chain is really for any camera system. It's just not for space imaging. And again, I use my dogs when I can in my pictures. So there's my corgi. But these are the key elements of the imaging chain that we will break down and understand and interrogate for every imaging system that we design for either commercial or for the government. But the key elements are, the radiometry, the light. Where does the light come from? How does it interact with the atmosphere if it's from space? How does it interact with the scene? How do you form the image? How do you sense the image? Is there motion involved that's going to interfere with the collection of that? And then the processing. And it used to be that most of the imagery then would be processed for display and human interpretation. Today, a lot of the data that we collect in space is not for human interpretation, it's for computer interpretation using artificial intelligence and machine learning algorithms as well. And that's a different processing. It's obviously not processed to optimize human interpretation, but optimized for computer interpretation. So when I say the links in an imaging chain, it's easy to talk about if I have a weak link in the imaging chain. For example, if I have a system that's out of focus, that is a weak link in my imaging chain and it will blur the image. If I'm taking a longer exposure compared to the motion that I'm moving when I take the picture, I'll get a motion blur called smear, and et cetera. So these just show where I have a weak link in my imaging chain that's dominant, and so it affects the image quality in different ways. And so the key is you want to balance all of those links so that you get the best image quality that you can. So we use this as a system engineering tool. If we want an image from space that looks like the one on the right, what is the system that we need to build that will capture that? And if we look at all the links in the imaging chain and put them together, especially the links within the camera system, now how do we put them all together to get the best image quality? And keep in mind that this could be 260 miles away flying at 17,000 miles per hour. And so again, you're going to need a large camera from that distance. It's not as simple as optimizing each parameter independently. You need to optimize them all together. One tool that has become very useful for us is something called image chain modeling. Today, we would call it a digital twin, but it's basically mathematically modeling the entire imaging chain so that when somebody gives us the design of an imaging system, we can put all the mathematics of that design into our computer model and output a picture that it would take as if it were flying and operating. And then we can tweak the design or actually look at different designs. And what you see on the right here are actually two different designs that we were considering for the ICONOS satellite. And you can see that design 1 is clearly superior to design 2. And this is just very valuable because if one design has a SNR of 60 and another design has an SNR of 40, a signal noise ratio of 40, is that a difference that you're going to care about when you look at the pictures? And until you create the picture and you actually look at it, you don't know if you care or not. And so we can work it backwards to actually help us set requirements for systems as well. And so just shamelessly plugging a couple of books that I wrote on it in the lower left here, if you're interested. This is just a very quick example of one piece of modeling the imaging chain that I think a lot of people can relate to. And if we mathematically model how light propagates and diffracts through an optical telescope, we can actually model what that image signature will look like. And so if I use an example of the Hubble Space Telescope that's imaging a star, which is basically a point of light, how do we model and what's the impact of what that star will look like in the image as the wavefront of light hits the different parts of the optical telescope? And so if we just consider the circular aperture, it's going to look like a ring pattern. Again, just at one wavelength of light. We have a secondary mirror that's going to block part of the aperture, and that changes the ring structure. I have struts that hold that secondary mirror in place. And so if you're looking down the aperture of the Hubble telescope, you're going to see this cross pattern, and that changes how the light spreads and diffracts through the telescope. And then if you integrate all of the wavelengths together to get the black and white image that Hubble gets, you'll get this cross pattern on top of the star. And that's actually what you see in the Hubble Space Telescope images, is you see stars with all of these cross patterns. And that cross pattern is from the light diffracting off the struts that hold the secondary mirror in place. And we can do the same thing with the James Webb Telescope. Again, sharp edges that light has to diffract and spread from will create line features. And so you see, because the James Webb Telescope aperture isn't round, we get this star pattern, this X and cross pattern in the images that we see in the James Webb Space Telescope. And again, I mentioned we use this for specification purposes. We can look at the image quality and say, well, how well do I need to maintain a temperature in the telescope so that the struts don't contract or expand under temperature changes and drive the system out of focus. And so we can actually do image simulations using the image chain model to see when we care, and that will help set requirements. So this is just the last design I'm going to talk about, the last design parameter. There are two limiting fundamental limitations of the resolution you will get in a digital camera system. One is from the light spreading through the optical system, the optics diffraction, and the other is the detector sampling from the digital detector itself. And so those two will both impose fundamental limits of the resolution. So again, you just see the mathematically on the right. But if we just talk about, well, what can we do to improve each of those resolutions? For optics diffraction, I can image at a shorter wavelength. I can use a bigger aperture, or I can get closer to the object. To get better detector sampling resolution in my image from the scene, I can reduce the sample distances in the detector. I can use a longer optical focal length, or I can get closer to the object. And you see, the one thing that improves both resolutions is getting closer to the object. And that's what we do, right? We always push our camera closer to the object to get a better resolution image when we want. And that's because what you're actually doing is improving both of these resolutions when you get closer to the object. There's a fundamental parameter that we call Q that shows the balance between these two resolution limitations. If it's this Q factor is 2, it means I've balanced them. And again, it means I've balanced the two limitations. What's interesting is that when you look at all the systems that we build, we don't build them at a Q equals 2, which means we aren't balancing the resolutions of the two. Basically, our satellites, we build them around Q1. If you look at your commercial cameras, your iPhone is a Q.8. Your digital Canon camera is a 1. A Google Pixel 6 Pro is a Q01. So everybody's building these systems where they haven't balanced the two resolution limitations. And why is this? And this causes a lot of debate in the community. I'll explain why in a second. But it actually, to my benefit, it actually got me to a congressional intelligence hearing where I had to testify what this is and why we build them this way. And actually got me to the White House Situation Room where I had a discussion with the National Security Council staff on why we build them this way. So I've actually had fun making the rounds telling the story. But long story short is if you balance the two limitations, you're still going to find that you don't get the best image quality. And in a nutshell, if you oversize the optics, so you're actually capturing better optics resolution that the sensor is going to throw away, you actually get better image quality. You'll get brighter images. They'll be less susceptible to motion and jitter. You'll get sharper contrast in the images. And so if image quality is the end game, then you're not going to mathematically balance those two resolution limits. So this is my last example before I leave you. Now that we know all about resolution and how to model it and where it comes from, this is something that I was seeing a lot in detective shows like CSI, and you see it in the movies, and it's the famous zoom and enhance example. And this is an example in CSI where you see in the photo lab, they're zooming in on this digital picture. They zoom in on the girl's eye, and they can see the reflection in the girl's eye. And you can see here's the girl taking the picture in the reflection. And you can see somebody in the reflection who said they weren't there when this picture was taken, and they are there. You can see it in the reflection. So they caught her in a lie. And it absolutely amazed me how many people, including my mother, that thought the FBI did this all the time. And I had to explain, no, you don't do this. You can't do this. And so I thought, well, okay, I'm an image scientist. Let's have some fun with this. So let's try to recreate this, and let's see why you actually can't do this and what you can do if you want to do this. So the first thing I did was I said, okay, well, I'm going to take a picture of an eye. So of course, this is my Leonberger, which is a very large dog. I took a picture of my reflection in her eye. And if I zoom in, there I am. And there I am holding the camera. And you could probably identify me from the reflection. So that's not the issue. So you can take a picture of and zoom in on the eye to identify the reflection, the person from a reflection. The key here is the camera was only about 10 centimeters away from the eye when I took this picture. And when you see this in Hollywood, they're much farther away. So if I recreate this scenario, again, here's my corgi at the fish pond. I zoom in on his eye, I look at the reflection, and in the reflection, I can see that there's a person standing behind the girl taking the picture. And so let's analyze this through an image chain model to see why I can't zoom and enhance this and what I have to do if I want to zoom and enhance this. So again, and there's an ebook that I published that has all the details in it if you want the math and all the explanations. But in a nutshell, this consumer camera, for me to zoom and enhance, it would have to have detectors that are too small to store electrons and a lens F number too small to form an image. If I want to create a camera that can do this, the easiest thing I can do is scale up the camera, and then I won't run into these two limitations. But from my graphic here on the right, you'll see the camera, I'd have to scale up the camera so that it's larger than my house. But if I scaled up the camera design to this size and then took this picture of the dog at the fish pond, I would indeed be able to zoom and enhance, zoom in the reflection and see this detail in the reflection if I did that. And that's why we build these cameras for our satellites so large, is because we're essentially doing the zooming and enhancing from space over a very large distance. And so we need very large systems that can do this. So the last thing I'm going to point out is the enhanced part. People talk about super resolution algorithms. Super resolution algorithms do exist. They try to estimate what the resolution was in the actual scene that the camera didn't capture. And so this is an algorithm that we work with called PMAP. This is an algorithm that we work with the people to help develop. And here I'm just trying to zoom by a factor of 4. And you can see that it actually produces more detail in the image than if I just interpolated the image up by a factor of 4. So there is some benefit there. But remember, in the example I just showed you, I have to zoom this in by a factor of 200 in order to do the zoom and enhance. And what's interesting is if I actually capture this image at 4 times better resolution, in the reflection, you would actually see that there's 2 people. But so both through interpolation and through the super resolution algorithm, I did not enhance it to the equivalent of capturing an image with 4 times better resolution because I can't see there's 2 people in the reflection. And so clearly this is a fail. And again, that's only a factor of 4, and I really know to go by a factor of 200. So this, again, this process has some advantages, but it's very limiting. Certainly not for Hollywood. And that's it. That's the end of my presentation. Hope you enjoyed it.
Thank you.
Thank you.
Just
That was-
enjoyed. I was blown away by all the detail and history and whatever. That was just phenomenal.
So Bob, I have a question for you. Nice seeing you,
yeah.
by the way. And
Yeah.
so, fads come and go. And like you said, super resolution is something, but it's way less than what's advertised. What would you say to people that are claiming now that they're just going to take your blurred image and use machine learning to figure out what's in there?
So we actually looked quite a bit at that ourselves. And as you know, Jim, because for the people here, Jim and I have worked together for decades. So Jim and I actually worked on some super resolution stuff together. But it's always an estimate, right? And so I know one of my early experiences with super resolution was when people were in the late 80s and early 90s when fractals was big. And so everybody was using fractals they would model the scene with all the fractal elements and then expand on the higher resolution using fractals. Well, fractals assume things are self-similar, and so they repeat those patterns. But those patterns aren't always being repeated in real life. And so you got to be careful what's real and what's not. And so that's exactly what we find with artificial intelligence, is that it's only as good as what you're teaching the algorithm, and it's going to guess. And especially in the intelligence community that we work in, nobody wants a guess. They want to know. And there was a great example that I would show where back when we were developing super resolution algorithms, and I think it was around the late 1990s, where I had an image of an aircraft and you couldn't see the windows along the fuselage until we ran the super resolution algorithm. And then you could clearly see and count the windows along the fuselage. When you looked at an actual picture of this aircraft, there were no windows on the fuselage. And what it was doing was it saw correlated noise, and it thought, hey, I'm seeing a pattern in the correlated noise. It must be windows along the fuselage, and it put them in. And so it was very impressive that you could actually count the windows along the fuselage until you learned there were no windows on the fuselage. So this is the problem we still have even with artificial intelligence.
Thanks.
Thank you very much again, Bob. That was fascinating and nice to extend from the beginnings back to all the way to artificial intelligence.
I love giving presentations like this, so I want to thank you for the opportunity.
Thank you very much. That was very good.
All right,
Yeah,
thanks.
nice to see everybody.
All right.